Ladies and gentlemen, please welcome Brady Forrest.
Oh my God. What? To you and DJ, you're switched. Who's first?
I'm first.
Hey there, I'm Brady Forrest. Thank you all for coming out. This is the 4th or 5th Ignited I.O., and I think it's the biggest one. At least this year, we won't be hearing Jane's Addiction play during our Ignite. So thanks for coming out. We've got 12 great speakers. We're going to hear from a number of Googlers. And in case you've never actually been to an Ignite before, if you don't know what Ignite is, it's a geek event that has spread around the world. And it gives people a chance to share their ideas and share their passions in a highly structured format that really lets them to kind of bump up against constraints and become just a bit more creative in how they present their ideas. So each of these speakers gets 20 slides that auto-advance every 15 seconds for a total of just 5 minutes. So they've had to really condense their ideas down and really be able to drive them home. And normally this is done with beer at night. We don't have that right now, but I think you'll still really enjoy the show. As I mentioned, we've got 11 great speakers, and our first one is here to talk about hackathons. Please welcome up Chuki.
Hello, my name is Chuki Chen. I'm here to tell you how to win hackathons. I went to my first hackathon last year in September, and I won. That app is actually an app to teach people how to write Chinese, and it went so well that I decided to put it on the market. How many of you here have Android devices? All of you? Great. Go download it. I would really appreciate it. So after Monkey Ride, I went on to 3 other hackathons and won them all. So I figured that I'll share my tips with you. But first, what are hackathons? As this picture shows, just a bunch of people in front of computers, typing away, building some software. Usually there's a theme. Sometimes there are prizes. There are 3 types of hackathons, in my mind at least. The first type is the business model type, where not only you have to build software, you also have to show how you're going to make money. The second type is the complete opposite. You're there to help a nonprofit to build a technical solution. The third type, the type I love, is the API hackathon, where the sponsors will come dangling lovely gadgets in front of you so that you will build something to their API, and then they can showcase how awesome the API is. So the best way to think of that is Iron Chef. The API is your secret ingredient, and your job is to cook up something that looks good and tastes good. Now, how does a hackathon actually go? Usually, it goes like this. Come up with an idea, spend all day hacking along, building up your software, and then you get on stage, and you present, and you demo. Now, here comes the secret. There are arrows on this slide, but they're in the wrong direction. You need to work backwards. You need to think about the demo first, because that is how you show how awesome your software is. You need to figure out how much time you have and how you're being judged on. Once you figure out that part, then you're ready to dazzle your crowd. From there, work backwards. Figure out how much time you have. Don't think of it as, oh, I have a full-day hackathon. You need to eat, your Wi-Fi will go down, all kinds of stuff will happen. So count it in the number of hours. A full-day hackathon, I would say it's a 6-hour hackathon. So know exactly how much time you have, and then budget accordingly. Don't think of too much stuff to build. So the first step is then you need to study your secret ingredient. So in Iron Chef, you have your crab. In our case, we have APIs. Figure out what they do, but more importantly, what you can learn within that day and build something with it. Once you have those gathered up, you are finally ready to come up with your idea. Now, what makes a good hackathon idea is something a little bit not obvious. What do I mean by that? Well, if your idea is a dime a dozen, everybody's implementing that, well, you won't stand out from the crowd, right? But then, if there's something that is super out there, you don't have time to implement that. You have a very short amount of time during a hackathon. Besides, it's so complicated to explain that there's no way you can show it at demo why it's a cool idea. Once you have distilled a very simple idea that's awesome to show, go talk to the sponsors. Ask them, see if they think it's a good idea, and then ask for pointers. How can you get started? Which function should you call? Take shortcuts. The sponsors are there to help you. Another shortcut that you can take is only implement the thing that you are going to demo. I mean, sure, go ahead and build up the whole screen with 5 buttons, but just make one button work and demo that button on screen. And very importantly, seek help. Give yourself at most a minute if you are stuck, and then ask. Ask somebody. You can ask the sponsors, but you can ask people around you. Yes, it's a competition, but the spirit is to help each other, so just go ahead and ask and help others as well. Remember, focus, focus, focus. Yes, you're helping other people, but think about what are you going to demo and focus on that. Work on that. And one tip that I would give is make sure that you have a 1-hour alarm right before the demo. At that point, it's a real code freeze. You are not touching that code base. At that point, you need to rehearse your demo. Make sure that your projector is hooked up properly so that you're ready for showtime. Then you can get on stage, show that one feature, and dazzle the crowd. So if I may summarize the whole thing in just one single word, is demo. The whole day, think about what you're going to demo, focus on that, work backwards, and you will win. Thank you very much.
What do you think of when I say the word chaos and chaos theory? Is it a fantastic pickup line for scientists? Maybe how crazy and complex the weather is. But here's the thing. Every single one of you already knows about chaos theory. Think for a moment about if you were a quarter second early or late to some critical moment in your life, how radically different the world would be. That idea has been around science fiction, been around books, but how did it really come to be in terms of a science? Well, it starts with this fundamental question back in the early 1800s was, is Jupiter going to go careening off into the moon? Are we going to have the sun go crazy on us? Or the moon crash into the earth? It was such a critical problem that King Oscar II, for his 60th birthday, commissioned the first Oscar. And in that prize, he invited all the mathematicians and physicists to test out their theories and ideas. And 12 enters, and 3 years later, one of them had a magnificent 150 pages of equations, so they said, wow, it's so full of equations, you win. And the biggest part of it was he didn't solve the problem. He said, well, let me take the sun, the earth, and the moon and see what happens. But then a graduate student came along. And as the graduate student was looking at it, there was this problem. And they realized that with the math, this crazy stuff could happen. It was almost as if there was chaotic trajectories. And the problem would remain this way for nearly 100 years until Ed Lorenz would come along. And he was working on atmospheric models, and he put these models into one of the first computers and put in something like 3.17825 as one of the starting conditions. And one day he decided he wanted to get a coffee and didn't want to enter that, so he put in 3.12. And then when he looked at the results, it was the same for a little while, but then wildly, wildly different. So he took apart the computer, tried to figure out what the heck was wrong, see if there's any real bugs or roaches inside there, put it back together, the same thing happened. And what he realized is that the world with weather is incredibly interconnected. And this idea that a butterfly flapping its wings in one part of the world could cause a tornado on the other side was born. And the problem, once again, would stay this way because nobody knew what to do with it. And it would stay this way for 10 years until Jim York would come along. And Jim had two fantastic things going for him. The first is he titled his paper, Period 3 Implies Chaos, thereby naming the field. The second is this new type of device that could sit on top of your desktop. The personal computer. Because now, for the very first time, he could put in those same equations Poincaré was working on. He could see the behavior that Lorenz was also seeing. All this rich behavior, the fractals, all that stuff that was coming about. And in fact, as they were starting to dig into it, they realized that there were very, very simple systems that would come about. Not like this table, but what's underneath the table. And this thing, which is like this very simple device, which is one of the first original ones to describe chaos theory. And you realize that you can get incredibly complex behavior out of such a very simple elementary system. And as they realized and dug into this, it was all over the place, all over the world, in math, weather, all over things. But as you get to this, there came a question. Well, great, what are we supposed to do with it? How do we actually think about it? And so a remarkable experiment happened in 1978. A satellite was launched named ISEE-3, and it had all these whiz-bang sensors and all this great stuff on it. But after a few years, it was running into a problem. It had only 2 spray cans worth of propellant left. But the guy said, hey, you know what? We've got this comet coming out. It's all got all the right sensors. We don't have time to build a new satellite. Why don't we try to fly this soon? And the guy said, 2 spray cans. That's all we got. But wait, this is the same problem Point created. A big planet, a small planet, and a tiny one. So 37 controlled burns later of spray paint. 5 lunar flybys getting as close as 80 miles to the surface of the moon. They were able to not fly through 1 comet, but through 2 comets using control of chaos. Let's get back to the weather. What can we say about chaos? If we know that there's small changes lead to big changes, why run one weather model? We should run lots of weather models. In fact, that's what we do today. We run an ensemble of them, and where the forecasts line up, we have a good forecast. Where they don't line up, we have bad forecasts. For the first time, this was used in the early 80s to predict one of the major snowstorms over the eastern seaboard. And what you can see over here is all that kind of spaghetti lining up over the East Coast. But you'll notice over the Atlantic, you've got horrible forecasts. And so when you listen to the weather these days and you hear this and they say, well, we're going to watch this, this is actually what they're looking at. And if I have to leave you with one thing, what chaos tells us is the world is incredibly interconnected. And that interconnectedness is really what drives the world. And from a sci-fi angle to now what you take as a science is something that lives in everyday life. Thank you.
And now, as they say, for something completely different. I am Chris Vian. I'm the Deputy United States Chief Technology Officer, and I'm here to talk to you about open innovation. Open innovation, what we're really talking about is how we're opening up government, making it more participative, collaborative, and enabling folks like you to help us solve problems. I think that I have the coolest job in Washington because I get to travel around the country, if not around the world, really looking at what's happening in an innovation space in the private sector, public sector, and extract kind of the secret sauce, the stuff that makes it all worthwhile. Actually, he's got the coolest job in Washington, especially today. But let me tell you that the president understands that the problems we face are just too great. We don't have time to use the usual ways of solving problems. We have to innovate. We have to use technology. Let me tell you about 3 problems. The first is that the population of the United States and the world is approaching $9.3 billion people in 2050. In May 23, 2007, that's when the world became the majority urban. And in the next 2 decades, we're going to be even 2/3 to 3/4 urban. The last stat that I've got for you is 12%. That's the arable land left on the planet that we can use to plant crops. So what this all means is that we have to double down, we have to use technology and figure out how we're going to make our current land more efficient in order to feed all those people. That's why the president says, and he said this to me many times, we need to think about how technology can be used to solve these problems, and we need to think about that every second of every day in order to do that. Blank screen. There we go. When I was Chief Information Officer for the City and County of San Francisco, I often worked on this problem of how do we reduce bureaucratic barriers? What could happen if government actually got out of the way and allowed citizens and hackers and everybody to really work on solving problems? This is what we've done with the data.gov platform, and I'm going to be talking about data from now on. We've actually open sourced the data.gov platform and made it worldwide in its applicability. Imagine if we had data from cities and counties and states and tribes and governments around the world all on the same platform. Imagine what we could do with that data, the problems that we could solve. And it's not something that we haven't tried before. Decades ago, NOAA released all of the data around weather, and the weather industry was created. The Defense Department did the same thing with GPS, and now we've got GPS everywhere. That all came from the government. So let me tell you about 4 current examples of what we're doing. With Blue Button, we are allowing vets to download their personal health care record and take that personal health care record wherever they go. And when it comes to energy, we're doing the same thing, but we're working with the private sector, and we're getting energy companies to let citizens download their personal data so that they can make better purchasing decisions. When it comes to education, a big topic these days, we're doing the same thing. We're allowing folks to start downloading their financial data. We're looking at releasing all of the new tools around learning registries and all of the educational data to help citizens make better informed decisions. The last example I want to talk about is safety. Tens of thousands of people die every year in traffic accidents. Imagine if we could get the data out of every vehicle that's involved in every one of those traffic accidents and extract it, what we could do. It's a model that's working, and what I want to tell you is what we're doing is we're taking groups of people, bringing them to Washington. We're focusing on solving problems in 90 days, and we're releasing the solutions. It's that minimum viable product that Eric Ries talks about. And one of the ways that we've actually put this on steroids is to develop the Presidential Innovation Fellows Program, where we're actually letting people sign up to come to Washington and help us work and solve some of these problems. But we know that that's not enough. We know that we need to make some structural changes in how the federal government works. We need to create government as a platform. We need to make everything API, and we need to make our data automatically released. So, here's my pitch. My pitch is that we need you, we're working with you, and we're creating opportunities for you to work with us from Washington to where you sit every day. As we release all of our projects and our data and our APIs, we ask you to help us come work with us and create the next generation of government. Thank you.
Kalispera, San Francisco. I'm John, I'm from Greece, and I'm going to talk to you about music, data, and how actually we geeks are rock stars. You have less than 5 seconds, I believe, to follow me on Twitter. Do it right now. So, we don't really know the origins of the music. Scientists believe that we started creating music in the moment we started to imitate the nature. I believe that we actually haven't created any music if you're listening to Justin Bieber, but whatever. So, as I said previously, I'm from Greece. So we Greeks, I won't say that we created the music, but the word music comes from muses. Muses actually were the goddesses of art, of inspiration, and everything. So we Greeks tried to correlate music and mathematics a long time ago. This guy Pythagoras, let me tell you a little bit about this guy. This guy was so obsessed with fractions. So one time that was passing through an anvil store, he realized that the size of the anvil determines how the sound actually, you can hear the sound. And that's how the diatonic scale, the 12 notes we have today were created. Now, moving a little bit forward in time, we realized that actually music tones are actually sound waves, and we can manipulate their altitude and tones and everything. So, of course, geeks took control and realized that we can create programs that we can manipulate sounds on the fly and creating electronic music and everything and interesting stuff. Actually, if you guys were here in Google I/O last year, sexy visuals, which were from Pixar, LucasArts, Apple, and Google, there were some guys that were creating music, live programming music on the fly. Yeah, and audio and visual was pretty cool. You should check them out. So, I'll tell you about my personal epiphany. My personal epiphany came the moment I realized that actually music is nothing more than data. And code is data, so data is music and all this stuff. So I started and implemented, like a proper geek, a language. A programming language where it enables you to write music in real time. The language is called MUD. It's based on Lisp, and it's using the processing framework, which is the best framework for audio and visual. So combining all this, we'll have some time. So here's the specification. We just play a pattern, and the pattern is a kick. So when you execute this one, you'll have the pretty clear, right? So by executing this, the kick is data, but it's also is music. It doesn't sound so much, so much right now, but give me a couple of seconds. So now we are adding kick, hi-hat, and tom. So if we play this pattern, you have the all together. Don't be afraid. Come on, guys. Okay. So let's try a little bit more, something more difficult. Now, let's say that we define a pattern that's actually musical notes. That the first example plays the na-na-na-na-na, a pretty easy scale. But if we apply data transformation, the reverse data transformation, we get the da-na-na-na-na-na. And of course, we can start writing some interesting tunes like the da-da-da-da-da-da-da-da-da. This is the Tron soundtrack. And it's pretty easy to, okay, it's not that easy, but you can see that actually music is data. And of course, if you're fans of dubstep, you can apply these functions, and you have the and all this strange stuff that dubstep is all about today. But imagine, music is actually data. So when I released the language, a guy came and told me, okay, but can you Bach? I told him, come on, man, I'm just a geek. I can't do that stuff. So this guy went a little bit crazy. So he started implementing all this in my programming language. And this is exactly the same thing. And this is the right hand. He also written the left hand, and he's playing all of them in unison and all this crazy stuff. And once in a while, he emails me videos of him playing Bach in his, he's in his house. Yeah, he's a crazy guy. So actually, data is music, right? So what if I get the latest tweets, I convert them to notes and play them? Guys, you won't believe that. This actually makes sense. If you go live on the site, on Matt's site, you'll see in a couple of slides, actually make sense. It's unbelievable. So, I was using processing framework I told you in a couple of minutes ago. You could use Overtone, it's another framework, again, built on Lisp. And of course, you could use Clojure scripts, so you can run everything on your browser. You could create this music on your browser. So let's disrupt a little bit music. So imagine that all albums are on GitHub, right? So you could clone them, fork them, make modifications, send them back. And also you could have revisions. You could share music as code. That disrupts everything. So we're building a band. Of course, we're geeks. We want to be rock stars, so we're building a band. If you're Skrillex or someone else, you please join us. Tweet, again, my Twitter. Follow it right now, guys. And let's rock. Thank everybody. Have fun.
We live in a world full of questions, deep philosophical questions, like, if I bike to work tomorrow, will it rain on me on my way home? What's Goog's ticker price going to be next week? And that cute brunette over there, what'll she be into, given the information on your public profiles? So I'm Thomas Park. I work for Google in Seattle on cloud computing. Before that, I worked a bunch of other places. And tonight, we're going to talk about solving these problems using technology. But before that, I'd like to make sure that we're all on the same page with regards to analytical modeling. So quick overview. You ready? Here we've got a bunch of data. It's two data classes, red and blue. If we want to build a model describing this data, we'll take about 70% of it, call it the training set, draw a line along the geometric median such that blue's on one side, red's on the other side for the most part. And then we can evaluate the performance of this model by putting the data points in the rest of the data set through the model and comparing the red-blue result with the known result. Pretty simple. So now that we know all about analytical modeling, let's talk about machine learning. So this is the application of algorithms to find interesting patterns and groups in data, such as, for example, if we look at the shape, color, and texture of these mushrooms, will they be delicious, poisonous, or make me see funny colors? So let's turn up the heat a little bit. Let's say that Google is launching dating functionality. We're going to use the information in your G+ profile to find interesting people for you to meet. Now, there's a clear vector for abuse here. You can create a lot of profiles with a lot of interests and get a lot of hookups. So maybe the G+ team wants to use machine learning to detect whether or not a user creating an account is a bot. We can use variables like this. Now, one of the interesting things about machine learning is that it still requires human intuition. It's easy for you and I to look at these and see that one of these is not a very plausible email address. So we need to extract features from these, such as, do Google hit results exist for the name, and are the letter sequences possible? So now I want to talk to you about something called random forests. Please raise your hand if you're familiar with these. Now, it's a pretty powerful technique. It's been around for about 15, 20 years, but almost nobody's heard of it. So I'll spend the rest of my talk focusing on random forests. What are these in a nutshell? The idea is that instead of building a really great model, we're going to build a large number of crappy models, kind of like our red-blue classifier. We'll let them vote, and then take the aggregate, or the average across all the models, and then that'll give us actually pretty good behavior. So how's this look in practice? We're going to use a large number of variables, ideally much more than what I have here, and build decision trees that fit this model exactly. Each of the decision trees is going to use a small random subset of the data. That's the random in random forest. Why is this interesting? So what we'll see is that we're building models that work okay for a lot of data, but in some cases, since we're building these models from observed data, we'll have variables that are very predictive, and so they'll work really, really well. Except for when our user's script decides to stop advertising its user agent as libdub_perl. So now the performance of Model 1 has tanked, but in an ideal situation, we'd have enough models that still perform well that will get good overall results. Now, in a real-world situation, we'd be using a very large number of these trees, hundreds more, each using maybe 5 to 10 variables. It's interesting to note also that these trees are totally independent. We can grow them and evaluate them in parallel. Not all machine learning algorithms can do this. That's cool. So let's talk a little bit more about variables. Most of these require human intuition, like I said, but random forests will help us out there as well. You also notice that we're not using variables with a huge value space like IP address, raw IP. There's just too many values, too much noise. So in a situation like this, we can use something called binning, where we separate the data out into categories that make more sense. If you guys have answered surveys that ask your age, it'll often say like under 18, 18 to 24, et cetera. Now, when we're feeding data to the trees, one of the cool things about the random forest algorithm is that it can actually tell us what variables are predictive. So we can feed it a lot of data without necessarily caring too much about whether or not it's a good variable. So we've been talking mostly about using random forest as a classifier, a binary classifier, is bot, is not bot. But it can also be used to recognize interesting groups of data, which in our dating case might be interesting people for you to meet. So 15 seconds less, how does this work? When we are running data through our models, we're going to see what terminal node, what leaf node it winds up in. All of the data goes through all of the trees, so we can keep track of how often 2 data points wind up in the same terminal state, and that'll tell us how similar the data is. So hopefully I piqued your interest about machine learning and random forest there. I'd just like to thank Ignite for bringing me on to talk. And thank you to all the artists who've put your photos out there under Creative Commons. Thank you.
It was late on a summer night as I sat typing "your offer is too low" into Google Translate to sell my 10-gallon hat with the scorching flames particle effect to a Japanese man that I wondered, how did I get here? This is my story. When I was a noob, my friend Joe told me to kill cows in Lumbridge so I could train my combat and sell the hides for 100 GP each at the local bank. I thought I was going to be the richest player in RuneScape. I set off to collect 10 million of them. But when I got to the bank, I saw someone was selling them there for 50 GP each. At first, I thought I was going to lose all of my profit as I had been undercut. But then I realized that I could buy his hides for 50 GP each and then sell them for 100 GP each and make a quick profit. And this was incredible to 10-year-old me because I realized that I could make money by not actually gathering materials, but by simply buying low and selling high. And this is what got me into trading. Later on, I was on a quest, and I noticed an NPC that sold dragon daggers for 17K each, which I could poison for 1K each, and then hop to a PvP world and sell for 55K each. And this was an incredible profit for little effort. RuneScape implemented a grand exchange, which allowed players to not just shout outside of banks, but go to a building and sell their items and have trades match up automatically and have prices change according to supply and demand. And with this came grand exchange price graphs, which I analyzed to see that when items were at their lower price, so I would buy them up and cause the price to artificially rise to turn a quick profit. And this idea eventually led to clan merchanting, which was essentially the same thing, but involved a larger group of people to buy more items. However, the higher-up members of the clan would usually sell their items before the other people and would cause people to lose most of their profits. Now, RuneScape imposed a trade limit, which was a maximum of 60K in order to stop scamming and real-world trading. But to get around this, traders would add junk items, which had a market price value, but no actual real value, to change the price of the items. Flipping is essentially overbidding on an item and then underbidding on an item to find its price. Then you buy the item for 1 GP over the lower bound and then sell it for 1 GP under the higher bound so you can undercut everybody and make a quick profit. Now, there are two main types of items in RuneScape. There's useful and there's cosmetic. However, of course, there are higher level armors which cost a lot of money because they are useful, so they fall into that category. But there are a set of items which are the most important cosmetic items because they are discontinued. And since they aren't released, they aren't going to be released into the game anymore, they're only going to rise in the long term, even if they drop in the short term, as well as players getting enough money to buy them, increasing the demand of the item. Now, there are items like this not only in RuneScape, but in Team Fortress 2. And the currency in RuneScape is set in stone because they have gold coins. But in Team Fortress 2, it's much more based on arbitrage, which changes it quite a bit. So in Team Fortress 2, there's metal, keys, and buds, which are the primary currency. Buds were a promotional item released by Valve when Team Fortress 2 was released for Mac, and they are the preferred currency to be paid in unusuals. And there are 4 main ways to make money when trading unusuals. The first is to buy buds for $31, then sell them for 24 keys. Then sell the keys for $1.49 each, and make $4.76 per bud that you sell. And it may not seem like a lot, but it adds up pretty quickly. The second way is unusual trading, which is what I did. And it would take forever to explain it, but basically you buy the hats that have a good effect and that have the good class, as well as the specific hats that people want. But the main trick when dealing with unusual trading is to find people who actually want the hats and to be nice to them, because being an asshole loses you 99% of your trades. The third way that people made money is by idling, by setting up 10 or so accounts to collect the 5 to 7 items that Valve releases per week, and they would use the items they gather to sell them to get metal to buy the hats and stuff that they wanted. And the fourth way that people would make money, which is obviously the most frowned upon, is by finding people who don't know what their hats are worth. So it's essentially finding someone and scamming them for their hat, which you can sell for between $20 to $1.5K. And recently, Valve hired an economist whose name is Yanis Varoufakis, and he's been analyzing the economy from a real-life perspective by looking at equilibrium. And so far, he has most of it right, but he's still a bit of a noob. Thank you.
Hey everybody, I'm David Weekly. A number of years ago, I was 25, living in the city and looking for ways to throw awesome parties. So I did what any reasonable young gentleman would do, and I started finding some housemates that I could go and split a crazy mansion with in Hillsborough. We decided to call it Super Happy Fun House after the Happy Fun Ball from Saturday Night Live, and we resolved to go and throw crazy parties. So our very first party that we had about 150 people, including a California gubernatorial candidate, who I briefly ended up dating, and a film crew. And so it was pretty clear we were onto something. We should do it again. So we started throwing these parties once every 6 weeks. We had professional DJs. We had 2-story high banners to welcome people there. We had in-ground hot tubs. It was a lot of fun. 2 of my roommates worked at IDEO. So we had all kinds of custom-built stuff. Like a freezer, we custom converted into a photo booth. And yeah, that's Aaron Patzer from Mint.com. We even went ahead and built a custom dance cage that people would go and dance in. These parties were great, and they became very, very popular. So popular that by the time we got to the 9th one of these parties, more than 400 people showed up. They had cordoned off the surrounding 2 blocks. They had put the SWAT team on high alert, and we got into trouble. So the cops said, you need to stop throwing these parties. They wrote the landlord a pretty angry letter. So we were bummed out. We were thinking, these parties were great. They actually contributed to the fabric of society. People were getting to meet each other and connect with each other in meaningful ways, right? There was actually 6 couples who met at these parties who ended up getting married, right? So what can we do to bring people together that's not gonna, get the cops called on us again, right? So one of my really nerdy friends proposed something really interesting. He had been part of a LAN party scene down Los Gatos, and he suggested that we do something that's like a LAN party, but it's productive instead. It's LANing plus deving. So it's a party, a LAN party, and it's productive, right? So we'd have beer and Red Bull and fast internet and all that. So we had the very first super happy dev house in mid-2005, and we got about 15 people to go and show up between 7 p.m. and 7 a.m., and it was a tremendous success. I ended up coding the first version of Wiki, which ended up becoming a real company, between 1 and 8 in the morning. And so we said, let's do this every 6 weeks. And we did. And it got bigger and bigger and bigger, just like Super Happy Funhouse did. And by the time we had done 9 of them at my house, my roommates got really sick of, so a couple hundred nerds going and taking over the house all day on a Saturday. So we started rotating where we had them. And then by the time we got to the 30th dev house at Sun's Executive Briefing Center, which is now Facebook's global headquarters, we had people overflowing this facility. And I said, you know what I would hate to do at the end of the night? I would hate to go and kick you all out, but I'm going to need to, because otherwise Sun Security is going to get mad at me. So what if there was a place where I didn't need to kick you out? We could call it Hacker Dojo, right? And this could be a place that was open 24/7 for you to build whatever the hell you want to. You could wake up at 3 in the morning and be like, I want to go and build something cool. And we'd have fast internet and tables and chairs and not a whole lot else more. So after about 6 months of figuring it out and getting initial membership base, we opened Hacker Dojo at 140A South Wisman in Mountain View. I encourage you to come visit. It's open 24/7. We started getting more and more membership at $100 a month. We were able to very quickly make ends meet. We've leased out more and more parts of the building until now, today, we're the largest hacker space in the world. We've rented out the entire building, some 13,000 square feet. There are some minor difficulties we're still undergoing with the city in terms of $250,000 of renovations that we need to make to fire safety and all that. So your contribution be appreciated. But come on by, drop on by. Pinterest was actually started at Hacker Dojo. Dozens of companies have started there, right? It's a just tremendous community resource. What about Super Happy Dev House? We recently celebrated the 50th Super Happy Dev House's Super Happy Block Party. It was advertised by the mayor of Palo Alto. About 2,000 people showed up. We cordoned off a whole block of Palo Alto. It was tremendous just to see those many people building. Dev House has also been replicated all around the planet. I just came back from Singapore where they're doing one of their dev houses there. There have been dozens of dev houses down in Mexico. They're pretty easy to throw. You just get a bunch of people together and you hack all night long. It doesn't have to have a winner. It doesn't have to be a competition. Dev House has also inspired other Dev House-like events, things like Bar Camp that's been all around the world, corporate hackathons like Facebook, and here we see a bunch of kids going and doing a hackathon, right? Hack the Future is what that's called. So getting kids involved in coding and production. These things are really important because they inspire folks. They get folks started. Woz actually was first introduced to a computer at a very early hackathon some 30 years ago at the Homebrew Computer Club, right? That's where he got introduced to his first computer, right? So you can do this. Go build a hackathon, get a dozen people together in your room, and go copy Dev House. Thank you.
Hi, good evening. Everybody here, I'm sure, has a question that they dread answering. Whether it's at a conference or a party or a friend's wedding, it comes at you from nowhere and there's nothing you can do about it. So for me, that question is, what do you do? So the conversation will go something like this. What do you do? I'm a composer. Oh, well, what do you play? Oh, I don't really play an instrument. Okay, so what kind of songs do you write? Well, I don't really write songs. Okay, so what kind of music do you write then? Well, I'm not sure I'd really call it music. Interesting. I'm just going to go and get a drink. So the conversation doesn't always have to go like that, but generally speaking, if you want to have a nice quiet time at a party, tell them you're an avant-garde composer. So avant-garde composers have historically had this image of themselves as being on the bleeding edge of musical frontiers and breaking down barriers, sticking it to the man, all this kind of thing. But audiences, at least these days, have a sort of slightly different idea of avant-garde composers, definitely less than heroic. And that's a shame because there's a huge amount of really great experimental music out there. But the stigma sort of still remains. So why is that? Well, if we rewind a couple of hundred years, if you wanted to hear new music, you'd go to a concert. It was all about concerts and audiences and premieres. But as soon as recording technology came around, and I love recording technology, by the way, composers could then experiment till the cows come home in their studios, and they didn't have to show it for an audience. So studios became like laboratories, but the problem was that composers thought they could take that stuff out on the road, and it didn't go down so well with the public. So against that backdrop of experimental music, I'm going to share a few of my experiences with you. So I've been very interested the last couple of years in the relationship between music and the brain. So my wife's a neuroscientist, my drinking buddy's a neuroscientist, there's just brains all over the place. So I got to asking, well, what can we do with this? So I started working with the EEG signal and neurofeedback, and started developing with some neuroscientist friends what's called a BCMI, or brain-computer music interface. EEG is great. It's cheap, it's non-invasive, it looks cool. And so we started working on an installation that we got approached to do involving the internet. And we came up with this idea of redoing a classic piece from 1965. We called ours Music for Online Performer. So what we did was we streamed the live brain signal split between the 4 frequency bands over the web via open sound control to the UK into a concert space, which was hooked up to an Arduino interface that controlled robots that would play acoustic instruments in real time. We also had a live stream chat room going on where people could log in, they could comment. We even took requests. It was like, you know, more drum, okay, increase beta power. So it was a complex dynamic system which was kind of multi-level with social interaction and robots on the other side of the planet. So how did it sound? Well, I have to tell you, it sounded pretty terrible. It really didn't sound that good, and that wasn't the point. The point was that we wanted to show that we could connect all this stuff together and that it could work over an hour-long performance with various different time zones. But at the end of the day, this was a music concert, and our robots ended up sounding like that candy-making machine out of Charlie and the Chocolate Factory. So it was great proof of concept, but as a piece of music, maybe not so great. So we as artists, I think, want to get from proof of concept to what I would call proof of context. So what do I mean by that? Basically, that you as the audience shouldn't have to bring the context in with you. You shouldn't have to have read a book on experimental music in order to be able to kind of appreciate the output. So in our case, the context was a quartet of robots. Now, in a real quartet, the instrumentalists listen to each other, and they kind of put it all together, and they vibe off each other. So if we had just tweaked the algorithm a little bit so that the signals were listening to each other and not all playing at the same time, it would have had a better sort of musical context. So just to demonstrate the power of context a little bit, this is Bob. He's a theremin, and he's 2 oscillators heterodyning, and you probably recognize the sound. It's kind of this sort of sci-fi, kind of annoying sound after a while. But if we just tweak the algorithm ever so slightly by applying some musical rules, we can have a very different kind of sound, which, you know, Bob has a lovely singing voice now, so at least in my Western ears. So that's what I would call context. And in terms of what we're doing to do contextual music in the future, we're working on a project for next May, which will take music as emotion, and we're looking to output that in a more contextual way. So next time you see me and you ask me what I do, I'll hopefully be able to say, I'm glad you asked me that, let's get a drink. Thanks very much.
Hi, I'm Amy Jo Kim, and I have a confession to make. Although I design rating systems for a living, I hate competing with other people. What I love is collaborative gaming. I love working together to create something bigger than we could do on our own. When I first started working in the games industry, gaming meant competition. Here's a textbook example, a system where players engage in a conflict with rules and a quantifiable outcome. Well, that certainly describes some kind of games. Game theory can help us with this. It defines zero-sum games. Games where there's a winner and a loser. We're opponents. These kind of games are what most people think of when they think of games. Good examples are any war simulation, chess, Go, Polo, head-to-head battles, rank-ordered competitions, gambling, where you're playing either against other players or against the house. These are all zero-sum games. What I found as I worked in the games industry was that the games I was working on and loved didn't fall neatly into this definition. Ultima Online, The Sims, Rock Band, all of them were structured more around having fun together and not around pummeling your opponents. So I tried to invent a different definition, and I slowly realized what these were non-zero-sum games. Games where rather than opponents, we're partners. We win together and we lose together. Some examples are Double Dutch on the Playground, Pictionary, and other party games. Martial arts like karate, where you have social support for your personal progress. Any charity walk or event, these are all non-zero-sum games. And the reason that you should care about this is because the games industry is undergoing massive disruption. And that's creating big new opportunities for collaborative games and services, particularly those that target females. 3 trends are driving this. The first trend is ubiquitous connected devices. Games used to be played on consoles, but the shift to smartphones and tablets and mobile computing has disrupted this. That's where the action is now. That's where people are looking to play their games, and that's where they're spending more money. If you look at the overall games industry shown here, the overall industry is growing, but at the bottom there, that's console. It's flat. It's even declining. All the growth is coming from mobile and online. And it's not just living room consoles that are being disrupted. Portable gaming. Here you have a slide that basically shows portable gaming consoles' lunch being eaten by iOS and Android. Yeah, Android. These mobile computing devices are where people are more and more playing games, and they are bringing in a different and more mainstream audience. That's the second trend. Gamers are mainstream in all ages. Gaming has matured into a mainstream entertainment medium, and the audience, which is gender balanced and many ages, reflects that. Did you know, for instance, that the fastest growing demographic on Facebook is women 55 plus? And that 93% of kids 8 to 13 play games online, and they cite Facebook as the main place they do it. What's happening is people are playing games, and they're also getting on social media, staying up to date, sharing photos, which leads us to the third disruptive trend, mutual entertainment. More and more people are engaged in sharing content they and their friends have created. That's sucking time away from highly crafted experiences like traditional games. Look at the hours people are spending. Here what you see is games are popular, absolutely, very popular, but those hours are dwarfed by the hours people are spending on sites like Facebook, YouTube, and Twitter. If you look at Instagram, it's a great example of this mutual entertainment trend. It's a photo sharing app. It's got this addictive loop where you don't know what's coming next, and the likes and comments from friends give you a pleasing but unpredictable feedback loop. Draw something is another great example. You play with a friend. If you draw the right word, they guess it correctly, you both win. If they don't guess it, you both lose. It's non-zero sum. Great example of mutual entertainment. Now we know from recent studies in happiness that a way to make yourself reliably unhappier is to do social comparison. It's also very motivating, which is why everyone wants a leaderboard on their website, even when it's a really stupid idea. We also know from happiness studies that investing in social relationships will reliably lead you to be happier. Collaborative games can deliver this. It's a blue ocean market with a big audience of gamers, male and female, smartphones in hand, waiting for games that they can play together that will bring them together. There's a Zulu word, Ubuntu, that captures this non-zero-sum mentality. So the next time you're doing any project, gamification games, think collaboration first, see where it takes you. Thank you.
Hi, I'm Peter Norvig, and I taught a class to 100,000 students at a time. I started this off because I had written a traditional textbook, a textbook on artificial intelligence, and we were happy that my co-author and I were able to capture over 90% of the market for textbooks. And so that was great, but the experience of writing a textbook felt so limiting, because everything was stamped on paper, or you can now get an electronic version. It's stamped on PDF, and it's static. And I knew people were interacting with it in a non-static way. They were underlying the parts that they liked. They were underlying in a different color the parts that were confusing. They were bookmarking the important places. That was all happening, and I wasn't capturing any of that. So I wanted to get it back. Also, there were complex things like these charts that I created with data that I manipulated with a program. I learned a lot from that manipulation, and then all they see is the static paper. So I wanted to go beyond that. I wanted to give them that hands-on experience. So my co-teacher, Sebastian Thrun, and I said, we're going to do that. We're going to bring an interactive experience, more interactive than a textbook, and we're going to bring it to more people. We're going to bring it to thousands of people at a time. We didn't know how many we were going to get, but it turned out the answer was 160,000 people signed up. By the end of the class, 80,000 were 7-day actives, and 23,000 finished all the homework, did the equivalent of a complete Stanford class. Now, how do we deliver that? Well, we learned from Benjamin Bloom that one-on-one mentoring delivers teaching that's 2 standard deviations above the norm. So you deliver a regular class and you compare that to one-on-one, you get 2 standard deviations better. So we wanted to emulate that one-on-one experience. We saw Sal Khan had done a great job with short videos. The short 10-minute videos are better than an hour-long one. We wanted to go even shorter. So we went 1 or 2 minutes and then interspersed the questions. And it was ironic, I think, that in trying to disrupt regular education, we ended up being more like a traditional education, a traditional college, because we found that what's most important is the social experience, interacting with each other, not interacting with the online components. And these are some of the social networking sites that the students used and sort of spontaneously developed. They went out and used all these online tools so they can interact with each other. The thing I learned the most from was Teach for America, where I learned about teachers who did an amazing job in taking students who were 2 years behind grade level, and in 1 year they brought them all up to where they belong. Now, this was a shock to me because, you know, I had worked at Google for many years, and I thought what my role was is you take a hard question like that, and you do all this tough algorithmic stuff, and then you get the right answer. And I was proud that we can do that kind of thing. But then I realized, well, wait a minute. Getting the right answer, that's the easy part. The hard part is asking the questions, getting people motivated so that they want to engage and ask questions. Now, finally, this is a college transcript. It transmits about 48 bits of information per year. This is an iPod. It translates about 192,000 bits per second. So that's 1 trillion times more. By cost, it's 1 quadrillion times more. We can get more data by interacting online. We can duplicate this one-on-one experience. We can bring it to 100,000 students, but the real power is them interacting with each other, these 100,000 squared pairs of students working together in a community.
Hi, my name is Mike, and I want to talk to you about the invention of the wheel. As engineers, I think you will appreciate that if you look to nature, you are humbled, essentially. Nature has come up with helicopters and submarines and color screens and high-speed cameras and all that stuff. But one invention, to me, that is typically human is the wheel. We've used wheels since the beginning of our civilization, and they've really driven a lot of the progress that we've made, and we've made them small, and we've made them big, especially in the production of energy. For example, this one is 30 feet across and produces electricity for millions of people in China. So the question I asked was, okay, so how does nature produce its energy? And to find out, we need to look at some cells. This is, for example, these are protrusions from cells in your ear that allow me to hear me right now. So let's take, for example, a muscle cell, cut it open, look at it with an electron microscope. And so on the right, there's the nucleus of the cell. The fibers at the top are the actual muscle fibers. And then the green blobs are mitochondria, where all the energy gets produced. And you only know you have to eat food, you breathe oxygen, and you exhale carbon dioxide. And of course, there are no fires inside your body. Instead, what happens is that your body breaks down that reaction into small steps using enzymes. And in each step, the energy released by the oxidation is coupled to the production of a molecule called ATP. And that molecule, which will come up in a minute, acts like a battery, like a common currency of the body. You can charge it, and you can discharge it somewhere else and use the energy to do whatever you need to do in the body. Let's see, where are we going from here? Right, okay, enzymes. Enzymes are proteins. Proteins are molecules that are very large, that are made from small molecules called amino acids. And these are strung together basically in a linear fashion, just like there. And then they fold up in these very complicated shapes that are determined by the sequence of amino acids that were put together. And so the previous picture is very complicated. If I redraw it like this, you can sort of see how the chain sort of folds up in this very, very interesting shape. And that was a very small protein. Typically, proteins are much, much larger like that one. But the same principles apply. There's a sequence that determines the structure of the protein, and the structure determines what it does. How does the cell know which order to put these together? It basically reads them off the DNA. That is, in fact, what DNA does, mostly. So it reads off the sequence, it makes the protein, and it folds up. How the sequence determines the structure is actually one of the big, unknown, unpredictable phenomena of biochemistry. It's very computationally intensive, and actually at Google here we've done a bunch of stuff on G-compute to try and get around that problem. Okay, so back to mitochondria. So when you burn food, what happens is that all of these different reactions pump protons into a space between two membranes in these mitochondria, so that it doesn't matter what reaction it is, it all ends up in this common currency of proton pressure. And then what happens is that pressure that gets built up flows out of this interstitial membrane space through this molecule there. And that's a very big protein that people have examined, and it wasn't clear for a while how it works. We knew that the protons were leaving on the bottom, they were going through the membrane, and somehow this was powered to the production of ATP at the top of this molecule. And how this coupling worked was not clear until a bunch of Japanese researchers did this really cool experiment. They drove the engine backwards, attached it to a glass slide, and then attached a fiber at the top that is big enough that you can actually see it. Remember, this is a single molecule. And what they saw when they looked down an optical microscope was this. This is actually the actual data from the paper. It basically rotates. It moves the fiber around in a circle. And there is a single molecule sitting at that axis. So more work basically showed that what is in fact happening is that this is a tiny, tiny turbine. The protons flow out through the membrane, and they make the bottom of the molecule rotate, and the rotation mechanically couples the energy to the production of this chemical molecule, sort of charging it with energy. And the way that works is essentially the camshaft inside of that molecule, once the molecule is bound and is reacted, the molecule is stuck. And so the camshaft pushes out the molecule so that it frees up the binding site for the next molecule. So in conclusion, oh, I should say, if you look at your hand right now, there are literally trillions of these turbines whirring away right now. And I'm afraid to say we're pretty late with the invention of the wheel, about 3.5 billion years. Thanks.
All right, thank you all for staying. Thank you to our speakers. Let's give them a hand. And as I mentioned, there are Ignites around the world, so definitely support your local chapter or just start one. You can contact me about that later. I'm Brady on Twitter. Take care.